Hello students, in this video we will start the topic group theory. So first we see what is a group. Group is basically denoted by G, compose, where G is a non-empty set and this is a binary composition. This thing will satisfy some property, then we will call this G equipped with the composition a group. So what are the properties? First property is G is closed under composition. That is, for any A comma B belongs to G, A compose B will be in G. So this is the first property. The second property is composition is associative. That means for any three elements A, B, C in G, first we compose A and B, then we compose it with C. This will be equal to this. That is, first we compose B and C, then we compose A with the result. So these two things will be same. This is the associative property. The third property is G has identity element. That is, there exists some E in G such that A compose E equal to E compose A equal to A for all A in G. The next property is every non-identity element in G is unique. Unique means what? For all A belongs to G, there exists an element, we call it as A inverse in G such that A compose A inverse equal to A inverse compose A equal to identity. If these four properties will satisfy, then we call this G compose a group. Let's see some example. First example is Z plus, where Z is the set of all integers, and here the composition operation is the usual addition. You can verify the four properties. See, the first property is G is closed under composition. You can take any element from Z and add them. That will be also an integer. The next property is associative. Take any three elements from Z and you can verify that this property will be satisfied. The third property is G has an identity element. So what is the identity element here? The identity element is 0. You add any element with 0. Suppose you have some A in Z. Okay, let's take some element, say 2. So 2 plus 0 equal to 0 plus 2 equal to 2. So 0 is the identity element here. Okay. Now the fourth property is every non-identity element in G is unit. That is, for all A belongs to G, there exists an element that we call A inverse in G such that A compose A inverse equal to A inverse compose A equal to identity. So suppose we take 2, then what is the inverse of 2 with respect to addition? That is minus 2. So you add 2 with minus 2, that is equal to minus 2 plus 2, you will get the identity 0. So all the four properties are satisfied here. So this Z comma plus is a group. Similarly, you can check that R comma plus, where R is the set of all real numbers. This is also group. Q comma plus, set of all rational numbers. This is also group. Okay. R comma dot, where dot is the usual product. This is also group. Here the identity element is 1. So all these examples are of group. Now you can see all these examples are of infinite group. Infinite group means the group where the number of elements are infinite. So these groups are infinite groups. Similarly, we have some finite groups also, like Zn comma plus. This is a finite group. What is Zn? So this is actually the group of integer modulo n. We will discuss about Zn in our future video. Just remember, this group is finite group. Also Sn. Sn is called symmetric group. This is also a finite group. Okay, so what is Sn? Suppose we have n numbers like 1, 2, 3 up to n. All the permutations of these n numbers is the group Sn. Okay, also we have the planes 4 group K4. This is identity A, B, AB. This is also a finite group. We will see all these examples in our next video. Just remember that these groups are finite. Now we will see what is commutative group. Commutative or abelian group. So what is commutative or abelian group? Suppose you take a group G, compose. Now you take any two elements A and B in G. What is abelian property? A compose B equal to B compose A. If this thing will happen for any pair of elements in G, then we call G is abelian group or commutative group. Let's see some example. Obviously, you can see that our Z comma plus, R comma plus, Q comma plus, all these groups are abelian. Okay, you can take any two elements and add them, just replace their position, you will get the same result. So these groups are abelian. Also, our finite groups like Zn, okay, K4, these groups are also abelian. But our symmetric group Sn, this is not abelian. Why? As example, take n equal to 3. So we have S3. So what is S3? S3 is identity 1, 2, 2, 3, 1, 3, 1, 2, 3, and 1, 3, 2. These are the elements of S3, the permutations of the numbers 1, 2, and 3. So you can take any two elements. Suppose you take 1 2 and 1 2 3. Now do their product. 1 2 1 2 3. So this is what? 1 2 3 1 3 and 1 2 3 2 3 1. Now how will do the product? So 1 goes to 2, 2 goes to 1. So 1. 2 goes to 3, 3 goes to 3, 3. 3 goes to 1, 1 goes to 2. So 2. So this will be 2 comma 3. Now we replace their positions. So 1 2 3 1 2. That is equal to 1 2 3 2 3 1 1 2 3 2 1 3. Then what will happen? 1 goes to 2, 2 goes to 3, 3. 2 goes to 1, 1 goes to 2, 2. 3 goes to 3, 3 goes to 1, 1. So this is equal to 1 3. See, the products are different. So S3 is non-abelian. But if you take S2, that is equal to E comma 1 2, only these two elements, you can check this S2 will be abelian. So try this example and verify that S2 is abelian. So from this example, we get a result, that is Sn is non-abelian for n greater or equal to 3. This is all for today's video. In the next video, we will see some more examples and some properties of group. If you like this video, please like and share to your friends and subscribe our channel, Higher Mathematics Academy. Thank you.